Welcome back. Today we're diving into the fascinating world of organic chemistry, specifically the reactivity principles of carboxylic acid derivatives. We'll explore how the structure of molecules like anhydrides, esters, and amides affects their reactivity, the impact of steric and electronic effects, and how strain in cyclic derivatives like lactams and lactones plays a crucial role in their chemical behavior. So, let's get started. When we talk about nucleophilic substitution reactions, the reactivity of a carboxylic acid derivative is determined by its substituents. Here's how it works. Anhydrides are the most reactive. Their resonance stabilization and the presence of 3 electron-withdrawing oxygen atoms make them highly electrophilic. Esters and carboxylic acids come next, with esters being slightly less reactive because they lack 1 electron-withdrawing carbonyl oxygen. Lastly, amides are the least reactive because they have an electron-donating amino group, which reduces their electrophilicity. Understanding this hierarchy helps explain how different derivatives behave in various reactions. Next up, let's talk about steric hindrance, which refers to how the size of substituents can block a reaction from occurring. For example, SN2 reactions won't happen at a tertiary carbon because the bulky groups around the carbon block the nucleophile from accessing the reaction site. However, we can use steric hindrance to our advantage. In SN1 reactions, a tertiary substrate is actually preferred because the bulky groups stabilize the intermediate carbocation. Steric hindrance is also useful when we want to protect functional groups during synthesis. For example, we can protect a carbonyl group by converting it into a non-reactive acetal or ketyl. After completing other reactions, we can regenerate the carbonyl by treating it with an aqueous acid. This technique is key in controlling reactivity in organic synthesis. Now let's dive into electronic effects. One such effect is induction, which refers to the distribution of charge across sigma bonds. In molecules, electrons are drawn toward more electronegative atoms, creating a dipole. This is why carbonyl groups have a partial positive charge on the carbon, making them susceptible to nucleophilic attack. The reactivity of anhydrides, esters, and amides can also be explained by induction. Anhydrides have 2 electron-withdrawing groups, creating a significant partial positive charge on the carbonyl carbon, making them more reactive. Amides, on the other hand, have a less pronounced dipole because nitrogen is less electronegative than oxygen, making them less reactive. Another important electronic effect is conjugation, which refers to alternating single and multiple bonds in a molecule. This setup allows p orbitals to align and delocalize pi electrons, creating a cloud of electron density above and below the molecule's plane. A great example is benzene, where delocalized electrons create a stable structure with multiple resonance forms. Conjugation can also be established in carbonyl-containing compounds, like alpha, beta unsaturated carbonyls, or enones. This electron sharing stabilizes the molecule and makes it more susceptible to nucleophilic attack by allowing for the stabilization of a positive charge after bonding. Now let's talk about strain in cyclic derivatives, like lactams, cyclic amides, and lactones, cyclic esters. The smaller the ring, the greater the strain due to torsional strain and angle strain. For example, beta-lactams are 4-membered cyclic amides with significant ring strain. This strain comes from the compression of the normal sp3 angle of 109.5 degrees, and it also reduces resonance in the nitrogen atom. These factors make beta-lactams highly reactive, which is why they're a core structure in antibiotics like penicillin. Many bacteria have developed enzymes called beta-lactamases to break down the beta-lactam ring, which is why beta-lactamase inhibitors are often used in combination with these antibiotics to enhance their effectiveness. In summary, understanding reactivity principles in carboxylic acid derivatives helps us predict how these molecules behave in reactions. Whether it's steric hindrance, electronic effects like induction and conjugation, or strain in cyclic compounds, these concepts are crucial for mastering organic chemistry. If you found this video helpful, give it a thumbs up, share it with your friends, and subscribe for more chemistry content. Don't forget to check out King of the Curve for interactive learning tools to help you ace your studies. Thanks for watching, and good luck with your chemistry journey.